You've felt gravity your whole life, but you've never really met it. Right now, an invisible force is pinning you to Earth at exactly the strength needed to shape your body, your time, and your fate. Change your location, and that force changes everything. On the Moon, you'd float. On Jupiter, you'd be crushed. Near a black hole, time itself would slow to a crawl. This is the story of gravity, not as a simple law, but as the force that controls the universe. I'd be grateful if you'd subscribe and softly support the video. Now let's get into it. Your body is a product of gravity. Every bone, every muscle, every system that keeps you upright, it all developed under the constant pressure of 9.8 meters per second squared. That's the acceleration pulling you toward Earth's core every moment of your life. But you don't think about it. You can't feel it any more than a fish feels wet. Gravity is the water you swim in, the invisible architecture that holds your entire physical existence together. And yet when you remove it, when astronauts float aboard the International Space Station, the body starts to fall apart. Not immediately, not catastrophically, but steadily, quietly, like a building losing its foundation one brick at a time. Within the first month in space, bones lose 1 to 2% of their density. The skeleton, no longer needing to support weight, begins breaking itself down. Osteoclasts, cells that normally clear away old bone tissue, keep working at their usual pace. But osteoblasts, the cells that build new bones, slow down. The balance tips. Breakdown outpaces growth. 6 months in orbit, an astronaut's bones can show the same weakness as an elderly person with osteoporosis. The weight-bearing bones, hips, spine, legs, suffer the most. Some astronauts have lost up to 20% of their bone mass in the bones that used to carry them through their days on Earth. The numbers are stark. Hip bones lose about 1.5% per month. The spine loses 0.9%. The heel bone, which bears your full weight with every step on Earth, can lose up to 2% monthly. After a year in space, some astronauts have bones equivalent to someone 30 years older, and the muscles follow the same path. Without gravity constantly pulling them down, the body decides it doesn't need all that strength anymore. Leg muscles atrophy. Core muscles weaken. Even the heart, which usually pumps blood uphill against gravity all day, finds its job suddenly easier. It starts to shrink. The cardiovascular system, built for a 1G world, doesn't know what to do with zero. Astronauts can lose up to 20% of their muscle mass in just 5 to 11 days. The soleus muscle in the calf, a postural muscle that works constantly on Earth just to keep you standing, atrophies faster than any other. On Earth, it's always working. In space, it's unnecessary. Blood shifts upward, pooling in the chest and head. Faces puff up, legs thin out. The pressure inside the skull rises, pressing against the backs of eyeballs, affecting vision. Some astronauts return with permanent vision changes because their eyes spent months being squeezed by fluid that had nowhere else to go. The condition has a name: spaceflight-associated neuroocular syndrome. The elevated pressure can flatten the eyeball, slightly changing its shape. The optic nerve can swell. About 40% of astronauts on long-duration missions experience measurable vision changes. Some need glasses for the first time. Others find their prescription has changed. On Earth, gravity gives you a job. It forces you to work just by existing. Every time you stand, walk, or even just sit upright, you're resisting that 9.8 meters per second squared. Your muscles fire. Your bones compress and rebuild stronger. Your heart pumps harder. You're in a constant invisible workout. In space, that job disappears, and your body, ever efficient, starts downsizing the workforce. That's why astronauts on the ISS exercise 2 hours every day, treadmills with harnesses to simulate weight, resistance machines to pull and push against. It's not optional. It's survival. Without it, they'd return to Earth, unable to stand under their own weight. The equipment has to be specially designed. Regular treadmills won't work, there's no gravity to keep you on the belt. So astronauts wear a harness connected to bungee cords that pull them down with adjustable force. They can simulate anywhere from 60% to 160% of their body weight. And even with all that, exercise recovery takes time. Blood volume restores in a few days. The body gets thirsty, drinks more, urinates less. Muscles come back within a month or so. But bones can take years. Some astronauts never fully recover the density they lost. The rule of thumb: 1 day of recovery on Earth for every day spent in space. Scott Kelly lived on the ISS for nearly a year, 340 days. When he came home, his body needed almost a year to remember how to be heavy again. His balance was off. His muscles were weak. Standing made him exhausted. Here's the strange part: gravity on Earth isn't even perfectly uniform. If you weighed yourself at the North Pole, then flew to the equator, and weighed yourself again, you'd be about 0.5% lighter. Not because you lost weight, but because Earth isn't a perfect sphere. It bulges at the equator and flattens at the poles. That bulge puts you slightly farther from the planet's center, where gravity is a bit weaker. The difference is about 21 kilometers. Earth's equatorial radius is 6,378 kilometers. The polar radius is 6,357 kilometers. That extra distance at the equator means you're farther from all the mass pulling you down. And Earth spins. At the equator, you're moving at over 1,600 kilometers per hour, racing around the planet's axis. That rotation creates a centrifugal force, not enough to fling you off, but enough to counteract a tiny bit of gravity's pull. The combination means someone standing in Kuala Lumpur experiences slightly less gravitational acceleration than someone standing in Oslo. The difference is tiny: 9.78 meters per second squared at the equator, 9.83 at the poles. Your body can't feel it. A standard bathroom scale wouldn't catch it, but precision instruments can measure it clearly. Even altitude changes it. Climb to the top of Mount Everest, 8,849 meters above sea level, and you'll weigh about 0.28% less than you did at sea level. Not because you're lighter, just because you're farther from Earth's center of mass. Geological features matter too. Stand over a dense ore deposit or a mountain range, and local gravity increases slightly. Stand over a less dense sedimentary basin or ocean trench, and it decreases. Geologists use these tiny variations to map what's underground without digging. The numbers are small, the changes are subtle, but they're real. Gravity is not the same everywhere on this planet. And yet to your body it all feels identical. Evolution built you to thrive in this narrow band of gravitational strength, this specific pull that happens to exist on Earth's surface. You're exquisitely calibrated to 9.8. Go significantly higher or lower, and everything starts breaking down. Before astronauts ever leave the planet, they train for what's coming. They fly in modified aircraft, Boeing 727s, Airbus A310s, on parabolic arcs. The plane climbs steeply at a 45-degree angle, then cuts its engines at the top of the arc. For 20 to 30 seconds, everyone inside experiences true weightlessness. It's not a simulation, it's actual free fall. The plane is falling toward Earth at the exact same rate as everything inside it. No force presses you to the floor. No weight pulls you down. You float, you drift. You can push off one wall and glide across the cabin like swimming through air. NASA calls the plane the Vomit Comet for good reason. About 1/3 of passengers get violently sick. Another third feel moderately ill. The final third handle it fine. The body, so used to gravity's constant tug, doesn't know how to process its sudden absence. The inner ear, built to detect up and down, sends confused signals. Nausea floods in. The vestibular system in your inner ear has 3 semicircular canals filled with fluid. On Earth, gravity always pulls that fluid down, giving you a constant reference for which way is up. In freefall, the fluid floats. The sensors fire randomly. Your brain receives contradictory information and interprets it as poison, hence the nausea and vomiting. But for those who can handle it, those 20 to 30 seconds feel like magic. Astronauts describe it as the closest thing to space they can experience on Earth. They practice moving in 3 dimensions. They learn to turn and spin without ground beneath them. They discover that starting a motion in 0G is easy, stopping it requires fighting your own inertia. The plane flies 15 parabolas in a typical session, 15 chances to feel gravity let go. Then it lands and weight returns like a heavy coat you forgot you were wearing. But even that free fall isn't true weightlessness, because gravity never actually disappears. Not at 4,000 meters, not at 400 kilometers, not anywhere in Earth's orbit. The astronauts floating on the ISS aren't weightless because they've escaped Earth's pull. At 400 kilometers up, gravity is still about 90% as strong as it is on the surface. If you could somehow stand on a platform at that altitude, you'd weigh almost exactly what you weigh right now. So why do they float? Because they're falling continuously, forever. The station races forward at 28,000 kilometers per hour, so fast that as it falls toward Earth, the planet's surface curves away beneath it at exactly the same rate. It's falling toward a target that keeps moving. It never hits. It just keeps falling. That's what an orbit is. Not an absence of gravity, just an eternal, perfectly balanced fall. And that falling feeling, that weightlessness astronauts experience, it's the same sensation you'd have if the floor suddenly dropped out from under you. They're not floating, they're plummeting. They just happen to be moving sideways so fast that they never land. But gravity itself, what is it really? For centuries, we thought we knew. Then Einstein looked deeper and discovered something stranger. Gravity isn't pulling at all. Space itself is bending. And the implications of that shift everything we thought we understood. Isaac Newton gave us the first real answer to what gravity is. 1687. His law of universal gravitation said that every object with mass attracts every other object with mass. The force depends on two things: how much mass they have and how far apart they are. Double the mass, double the pull. Double the distance and the pull drops to 1/4. Simple, elegant, and for 300 years it worked beautifully. It explained why apples fall, why the moon orbits Earth, why planets circle the Sunday. Newton's equations predicted the motion of everything from cannonballs to comets with stunning accuracy. His inverse square law was revolutionary. It meant gravity weakens with distance in a precise, predictable way. It meant you could calculate the force between any two objects in the universe if you knew their masses and separation. Earth pulling on the moon, the sun pulling on Jupiter, even your body pulling on the chair you're sitting in. The force is tiny, but it exists. But there was a problem. Mercury, the innermost planet closest to the sun, orbits in an ellipse, an oval, not a perfect circle. And that ellipse slowly rotates a phenomenon called precession. The point where Mercury comes closest to the Sun, the perihelion shifts slightly with each orbit. Newton's equations predicted how much it should precess based on the gravitational tugs from other planets. Venus pulling, Earth pulling, Jupiter's massive gravity adding its influence. The math said Mercury's perihelion should shift by about 531 arcseconds per century. Astronomers measured it carefully. 574 arcseconds per century. The difference 43 arcseconds. A tiny angle. 1 arcsecond is 1/3600th of a degree. 43 arcseconds is barely noticeable, even through a telescope, but it was real. And it was wrong. For decades, no one could explain it. Some thought there might be another planet closer to the Sun tugging on Mercury. They even gave it a name, Vulcan. Astronomers searched for it during solar eclipses, when the sun's glare wouldn't blind their telescopes. They searched. They never found it. Because the answer wasn't another planet. The answer was that Newton's picture was incomplete. In 1915, Albert Einstein published his theory of general relativity, and it changed everything. Einstein said gravity isn't a force at all. It's geometry. Mass doesn't pull on other mass. Instead, mass warps the shape of space and time around it. Objects moving through that warped space follow curved paths. What looks like a force pulling them is actually just them traveling in straight lines through curved space. The analogy everyone uses: place a bowling ball on a stretched rubber sheet. The ball creates a dip, a depression in the sheet. Now roll a marble nearby. The marble doesn't travel in a straight line anymore. It curves toward the bowling ball, circling around the dip, not because the bowling ball is pulling it, but because the sheet itself is curved. That's what mass does to space-time. The sun creates a deep well in the fabric of space around it. Earth rolls along the curved edge of that well, circling endlessly. Not because the sun is pulling Earth with an invisible rope, just because Earth is following the straightest possible path through curved space. But the analogy has limits. The rubber sheet is two-dimensional bending in a third dimension we can see. Space-time is four-dimensional, 3 dimensions of space plus one of time, and it curves in ways we can't visualize directly. We can only describe it mathematically. And Mercury, so close to the Sun, it experiences the steepest part of that curve. The deepest part of the gravitational well, where space-time is most distorted. Newton's equations, which assume space is flat, couldn't account for that curvature. Einstein's equations could. They predicted Mercury's precession exactly, 43 arc-seconds per century, precisely matching the observations. That was one of the first confirmations of general relativity. Einstein's theory made a prediction that Newton's couldn't, and nature sided with Einstein. But general relativity does more than fix Mercury's orbit. It reveals something profound about the universe. Time and space are not separate things. They're woven together into a single four-dimensional fabric space-time, and that fabric is flexible. It bends. It stretches. It curves in the presence of mass and energy. The stronger the gravity, the more space-time curves. And the more space-time curves, the stranger things get. Near Earth, the curve is gentle. Newton's approximation works fine for everyday life. Launching satellites, landing spacecraft, calculating trajectories. You don't need Einstein's full equations unless you want extreme precision. But go somewhere with intense gravity near a black hole, or inside a collapsing star, or even just close to a neutron star, and space-time curves so dramatically that Newton's picture breaks down completely. Time slows, light bends, the rules change. And here's the key insight: both Newton and Einstein are right. They're just describing reality at different scales. Newton's gravity works beautifully for weak fields, slow speeds, and small masses. It's simpler, easier to calculate. For almost everything we encounter in daily life, it's good enough. Engineers use Newtonian mechanics to design bridges, predict planetary positions decades in advance, and send spacecraft across the solar system. The errors are negligible. Einstein's gravity is the deeper truth. It works everywhere Newton's does, plus all the places Newton's breaks down. But the math is harder. The concepts are stranger. The equation's 10 coupled nonlinear partial differential equations require advanced mathematics to solve, even for simple cases. You only need Einstein when things get extreme. Strong gravity, high speeds, situations where space-time curvature becomes significant. Which one is real? Both. Neither. They're models. Maps of reality, not reality itself. And like all maps, they're useful for different journeys. If you're navigating a city, a street map is perfect. You don't need a globe. The curvature of Earth doesn't matter when you're deciding whether to turn left or right at the next intersection. But if you're crossing an ocean, that street map becomes useless. You need something that accounts for the curve of the Earth. You need a globe or a navigation chart that incorporates spherical geometry. Newton is the street map. Einstein is the globe. And the most beautiful part, Einstein's equations, when you simplify them for weak gravity and slow speeds, reduce exactly to Newton's law. General relativity contains Newtonian gravity as a special case. It's a limit, a mathematical approximation that emerges naturally from the fuller theory. Einstein didn't replace Newton. He zoomed out and showed us a bigger picture. Newton's gravity is still correct within its domain of validity, and that domain covers almost everything humans have ever experienced until very recently. But there's one place where even Einstein's picture is strange, where gravity doesn't just curve space, it curves time. The stronger the gravitational field, the slower time passes. Not metaphorically, not approximately, literally. Clocks on GPS satellites orbiting high above Earth, where gravity is slightly weaker, tick faster than clocks on the ground. Not by much, about 38 microseconds per day. But that tiny difference matters. GPS works by triangulating your position based on signals from multiple satellites. Those signals travel at the speed of light. If the satellite clocks were even a fraction of a second off, your position would be wrong by kilometers. The calculation is precise. General relativity says clocks in weaker gravity run faster about 45 microseconds per day for GPS satellites. But special relativity says moving clocks run slower. The satellites are moving at about 14,000 kilometers per hour, which slows them by about 7 microseconds per day. The net effect 38 microseconds per day faster. Engineers designing the GPS system had to account for relativity. They had to slow down the satellite clocks before launch, setting them to tick at 10.22, 999999954, 3 MHz instead of 10.23 MHz. That way, once in orbit, the clocks would appear to run at the correct rate compared to clocks on the ground. Without Einstein's corrections, GPS would drift by about 10 kilometers per day. After 2 minutes of turning it on, your navigation would be wrong by hundreds of meters. After a week, it would be useless. So every time you check your phone's location, you're using general relativity. You're relying on the fact that gravity bends time, and near stronger gravity, the effect becomes dramatic. On the surface of a neutron star, gravity is so intense that time runs about 30% slower than it does in empty space far away. If you could somehow survive standing there, which you couldn't, and you watched a clock floating in space, it would appear to be racing forward. Meanwhile, to someone watching you from that distant clock, you'd seem to be moving in slow motion. A year on the neutron star surface would be about 1.4 years for the distant observer. The difference accumulates. Stay there for a decade, and 15 years would pass in the outside universe. Near a black hole, it gets even stranger. At the event horizon, the point of no return time essentially stops. Light trying to climb out of that gravitational well gets stretched, redshifted, slowed down until it freezes. An astronaut falling into a black hole would cross the horizon in finite time on their own clock. But to someone watching from far away, they would appear to slow down, freeze, and fade, never quite reaching the edge. Both perspectives are real. Time itself becomes relative. So which picture is correct? Is gravity a force pulling objects together, or a curvature of space-time telling objects how to move? The answer depends on what you're trying to understand. For launching rockets and predicting planetary motion, Newton's force works fine. For GPS satellites and black holes and the shape of the universe, you need Einstein's geometry. They're not contradictions, they're layers. Different ways of seeing the same phenomenon, each revealing something true. But here's what both pictures agree on: gravity isn't uniform. It changes. Its strength depends on where you are and what's nearby. And on different worlds with different masses and different sizes, gravity becomes something almost unrecognizable. The same force that gently holds you to Earth's surface can crush matter into unimaginable density or let you float away with the slightest push. On the Moon, an astronaut can jump nearly 3 meters high. On Earth, the same person might clear half a meter. 6 times higher with the exact same muscle strength. That's because lunar gravity is 1/6 as strong as Earth's. The Moon has less mass, about 1/81st of Earth's mass, and a smaller radius. When you combine those factors using Newton's equation, you get a surface gravity of 1.62 meters per second squared, compared to Earth's 9.8. What does that feel like? A 70-kilogram person on Earth weighs about 11 kilograms on the Moon. The weight of a small dog. Every step becomes a bounce. Every movement feels effortless. The Apollo astronauts quickly discovered that walking normally was inefficient. Instead, they developed a hopping gait, the bunny hop, where they'd push off with both feet and sail forward in long, slow arcs. Dust kicked up by their boots would hang in the air longer before settling back down. Rocks thrown would travel farther. Everything moved with a strange, dreamy quality, like being underwater, but without the water. The Apollo 17 astronauts tested this. Eugene Cernan threw a hammer. On Earth, he might have tossed it 20 meters before it hit the ground. On the Moon, with 1/6 gravity and no air resistance, it sailed over 50 meters, tumbling end over end in perfect parabolic arcs until it finally touched down in the grey regolith. And when they drove the lunar roving vehicle, the Moon buggy, across the surface at 12 kilometers per hour, the wheels would lift off the ground on bumps. The entire vehicle would go briefly airborne, hanging in the low gravity for seconds before settling back down. On Earth, that same bump, at that same speed, would barely jostle the suspension. The astronauts had to relearn movement. Push off too hard, and you'd float for uncomfortably long. Turn too quickly, and momentum would spin you around. Your inner ear, calibrated for Earth's gravity, would send confused signals. Some astronauts reported feeling disoriented, not quite sure which way was up, even though the horizon was perfectly visible. But the moon still has gravity. Weak gravity, yes, but enough to pull you back down eventually. Enough to keep dust on the ground and rocks from floating away. Go smaller, and even that changes. Asteroids, those chunks of rock tumbling through space, ranging from a few meters to hundreds of kilometers across, have gravity so weak it barely qualifies as gravity at all. On asteroid Bennu, 500 meters wide and shaped like a spinning top, gravity at the equator is about 1/1,000,000th of Earth's. A 70-kilogram person would weigh about 70 grams, the weight of a large egg. Jump even slightly and you'd escape into space. Not orbit. Escape. The escape velocity, the speed needed to leave permanently, is just 20 centimeters per second. Walking pace. If you tried to walk normally, your first step would launch you off the surface. NASA's OSIRIS-REx spacecraft visited Bennu in 2020. When it descended to collect a sample, it couldn't land. Landing would have required touching down, and touching down would have meant bouncing off or even pushing the asteroid away. Instead, the spacecraft extended a robotic arm and gently tapped the surface for 5 seconds, just long enough to blow nitrogen gas and collect disturbed material. Then it immediately fired thrusters to push away before Bennu's feeble gravity could pull it down into a slow-motion crash. The images sent back showed something unexpected. The surface wasn't solid, it was loose. When the nitrogen gas hit rocks and dust exploded outward like a splash of water. The spacecraft's arm sank 12 centimeters into what mission scientists described as a ball pit, barely any resistance at all. That's why most asteroids aren't solid rocks. They're rubble piles. Millions of years ago, something big hit an asteroid and shattered it. The pieces flew apart, but they didn't fly far. Gravity, though weak, still existed. Over time, decades, centuries, maybe millennia, the fragments drifted back together, not fusing, not compacting, just piling up. The result is a loose collection of boulders, stones, gravel, and dust, all weakly held together by their collective gravity. No internal strength, no cohesion, just gravity barely winning against the forces trying to tear it apart. And they do tear apart. If an asteroid spins faster than about one rotation every 2.2 hours, centrifugal force overcomes that feeble gravity. Rocks on the surface fly off into space. The asteroid sheds mass until it slows down enough to hold itself together again. Observations confirm this. No asteroid larger than about 150 meters across has ever been observed spinning faster than that critical threshold. They can't spin faster, and they self-destruct. Smaller asteroids under 100 meters can spin faster. Those are probably monolithic, solid chunks of rock with enough internal strength to resist flying apart. But anything bigger, probably a rubble pile, a gravitational aggregate pretending to be a world. The Japanese spacecraft Hayabusa 2 visited asteroid Ryugu in 2018. Images showed a surface covered in boulders, some as large as houses, just sitting there. Not embedded, not cemented. Just resting on top of each other, held down by gravity measured in microgravities. Touch one with any force, and it would drift upward like a balloon. When Hayabusa 2 deployed small hopping rovers to the surface, they had to be careful. Too much force from the deployment mechanism, and the rovers would have escaped into space. They descended slowly, touched gently, and even then, each hop covered meters of distance and lasted minutes. Now go the other direction. Go bigger. Much bigger. Jupiter, the largest planet in the solar system, 318 times Earth's mass. Big enough to fit 1,300 Earths inside its volume. You'd think gravity there would be crushing, 300 times stronger than Earth's. But it's not. Jupiter's surface gravity, if it had a surface, which it doesn't, but the gravity at the altitude where atmospheric pressure equals Earth's sea level, is only 2.53 times Earth's. Why? Because Jupiter is huge. Its radius is 11 times Earth's, and gravity follows an inverse square law. Double the distance from the center and gravity drops to 1/4. Jupiter's mass is enormous, but you're standing much farther from that mass than you would be on Earth. So a 70-kilogram person on Jupiter would weigh about 177 kilograms. Heavy, crushing if you're not used to it, but not 300 times heavier. Still, that's enough to make life unbearable. Your muscles, built for 1G, couldn't support you. Your heart would struggle to pump blood against 2.5 times the normal resistance. Standing would be exhausting. Walking nearly impossible. You'd collapse under your own weight within minutes. Blood would pool in your legs. Your cardiovascular system would fight to push it back up to your brain. Every breath would feel like lifting weights. Your spine would compress. Vertebrae would grind together under the load. If you managed to stand for an hour, you'd be shorter when you lay down, compressed by the relentless pull. And Jupiter isn't even close to the most extreme. Saturn's moon Titan has surface gravity of 1.35 meters per second squared, about 14% of Earth's. Mars has 3.7, about 38%. Venus has 8.9, about 90%, nearly identical to home. Each world offers a different experience of weight. Each one reshapes what heavy means. White dwarfs, the dense remnants of dead stars, have surface gravity hundreds of thousands of times stronger than Earth's. A 70-kilogram person would weigh millions of kilograms. Their body would pancake instantly. Atoms themselves would struggle under the pressure. Neutron stars, billions of times stronger. Surface gravity so intense that mountains on a neutron star can't be more than a few millimeters tall. Any higher and the rock flows like liquid under its own weight. And the density. A neutron star packs 1.4 solar masses, nearly 300,000 times Earth's mass, into a sphere just 20 kilometers across, about the size of a city. The entire mass of the Sun compressed into something you could drive across in 15 minutes. At that density, a sugar cube-sized chunk weighs as much as Mount Everest. A teaspoon weighs about 1 billion tons, maybe more, depending on which calculation you trust. The numbers are so extreme they stop making sense. The matter inside isn't normal matter anymore. Protons and electrons get squeezed together so hard they merge into neutrons. The entire star becomes one giant atomic nucleus. Neutron-degenerate matter, held up only by quantum pressure, resisting further collapse. And it spins. Some neutron stars rotate hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446, spins 716 times per second. Its equator moves at about 24%, the speed of light. At those speeds, the star bulges at the equator, flattens at the poles. Spacetime itself swirls around, the spinning mass dragged along like honey stirred with a spoon. If you could somehow bring a teaspoon of neutron star matter back to Earth, which you can't but imagine it wouldn't stay compressed, the moment you removed it from the crushing gravity holding it together, it would explode. The neutron degeneracy pressure, no longer balanced by gravity, would blow outward like a bomb. A tiny sample could vaporize a significant chunk of the planet. Gravity at that scale isn't just strong. It's the sculptor, the architect. It decides what forms matter can take and what structures can exist. Here on Earth, gravity is gentle enough that we can build tall buildings, and mountains can rise kilometers high. Mount Everest stands at 8,849 meters because Earth's crust is strong enough to support that weight against gravity's pull. Go much higher and the rock at the base would start to flow plastically, unable to bear the load. On Jupiter, the atmosphere itself weighs so much, it compresses the interior into metallic hydrogen, a state of matter that doesn't exist naturally anywhere on Earth. Hydrogen, normally a gas or liquid, gets squeezed until the electrons separate from their nuclei and flow freely like electrons in metal. The pressure required is over 1 million times Earth's atmospheric pressure. That metallic hydrogen layer is thousands of kilometers thick surrounding Jupiter's core. On a neutron star, the surface is smoother than a billiard ball because nothing can stand tall against that pull. The strongest material imaginable, say diamond or some exotic alloy, would still flow and flatten. Gravity wins. Always. Every world is shaped by its gravity, and every gravity is shaped by mass and distance. But there's one place gravity gets even stranger. Deep inside stars, where it doesn't just hold matter together, it forces matter to transform. Where gravity builds furnaces hot enough to forge new elements. where the war between inward crush and outward pressure creates every photon of light in the universe. At the center of the Sun, 15 million degrees Celsius. Pressure, 250 billion times atmospheric pressure at Earth's surface. Density, 150 grams per cubic centimeter, 10 times denser than lead. In that inferno, hydrogen nuclei slam together hard enough to fuse into helium. Every second, 600 billion kilograms of hydrogen undergo fusion. 4 billion kilograms of mass vanish converted directly into energy, according to Einstein's equation. E equals mc squared. That energy, gamma rays, at first begins a long journey outward. It collides with other particles, gets absorbed and re-emitted, scattered in random directions. A single photon born in the core might take 100,000 years to reach the surface, bouncing through the dense plasma like a pinball through an endless machine. When it finally escapes into space, it's no longer a gamma ray. It's visible light, sunlight, the light that warms your skin and makes plants grow and powers nearly every process on Earth's surface. But that fusion, that light, that heat, none of it would exist without gravity. 4.6 billion years ago, there was no Sunday, just a cloud of gas and dust slowly rotating in space. Mostly hydrogen and helium, with traces of heavier elements forged in earlier stars that exploded long before. The cloud stretched across trillions of kilometers, thin, cold, nearly empty, density barely above the vacuum of space. A few hundred atoms per cubic centimeter compared to 10 to the 19th atoms per cubic centimeter in the air you breathe. Then something disturbed it. Maybe a shockwave from a nearby supernova. Maybe just the gradual accumulation of density fluctuations. Whatever the cause, one region of the cloud started collapsing under its own gravity. As it collapsed, it spun faster conservation of angular momentum, the same reason a figure skater spins faster when they pull their arms in. The cloud flattened into a disk. Most of the mass fell toward the center, piling up, heating up. Gravity doesn't just pull things together. It converts gravitational potential energy into thermal energy. As matter falls inward, it speeds up. As it slams into other matter, that kinetic energy becomes heat. The proto-sun grew hotter and denser. 1 million years passed. 10 million. The core temperature climbed. 1 million degrees. 5 million. 10 million. At around 10 million degrees, hydrogen nuclei start moving fast enough to overcome their electrical repulsion. They're both positively charged. They don't want to get close. But at high enough speeds, they collide despite the repulsion. And when they get close enough, within about 1 femtometer, 1 quadrillionth of a meter, the strong nuclear force takes over. The strong force is much more powerful than electromagnetism at short range. It binds quarks into protons and neutrons. And at these distances, it can bind protons to each other, fusing them into heavier nuclei. The process is called the proton-proton chain. 2 protons collide and fuse, forming a deuterium nucleus. 1 proton and 1 neutron, plus a positron and a neutrino. The deuterium fuses with another proton, forming helium-3 2 protons and 1 neutron, plus a gamma ray. 2 helium-3 nuclei collide, forming helium-4 2 protons and 2 neutrons and releasing 2 protons back into the mix. Net result: 4 hydrogen nuclei become 1 helium nucleus plus energy. Lots of energy. The mass of the helium nucleus is slightly less than the 4 hydrogen nuclei you started with. That missing mass, about 0.7%, becomes energy. 4 million tons of matter converted to pure energy every single second. Fusion ignites. The proto-sun becomes a star. And immediately, something changes. The fusion releases energy. That energy creates pressure, radiation pressure pushing outward from the core. For the first time, there's a force strong enough to resist gravity's inward crush. The sun stops collapsing. It reaches equilibrium. Outward pressure from fusion exactly balances inward pull from gravity. The sun neither expands nor contracts. It simply burns stable for billions of years. This balance is delicate, but it's also self-regulating. If fusion speeds up, maybe the core gets a little hotter for some reason. The extra energy makes the core expand slightly. Expansion lowers the density. Lower density means fewer collisions. Lower temperature means slower moving nuclei. Fusion rate drops back down. If fusion slows down, maybe the core cools a bit, gravity wins temporarily. The core contracts. Contraction raises the density. Higher density means more collisions. Higher temperature means faster moving nuclei. Fusion rate speeds back up. It's a thermostat, an automatic feedback loop. Gravity and pressure negotiate continuously, finding the balance point where they cancel out. That's why the sun has burned steadily for 4.5 billion years. That's why it will keep burning for another 5 billion. The fusion rate adjusts itself to whatever level maintains equilibrium. Every star does this. Red dwarfs, barely massive enough to ignite fusion, burn their hydrogen slowly and can last trillions of years. A star like Proxima Centauri, the closest star to our sun, has only about 12% of the sun's mass. Its core is cooler fusion, proceeds more slowly, and it will outlive the sun by a factor of 100 or more. Blue giants, dozens of times the sun's mass, burn ferociously and die within millions of years. Rigel, a blue supergiant in the constellation Orion, is about 20 times the sun's mass. It burns so hot and bright that it will exhaust its hydrogen in just a few million years, total a blink compared to the sun's 10 billion year lifespan. But all of them balance gravity against pressure. All of them regulate themselves. But equilibrium won't last forever. The sun is slowly running out of hydrogen. Every second, 600 billion kilograms less. It's been doing this for billions of years. The core where fusion happens is now about 65% helium. The rest is hydrogen that hasn't fused yet, plus trace amounts of heavier elements. As the hydrogen depletes, the balance starts to shift. Less fuel means less fusion. Less fusion means less outward pressure. Gravity starts winning. The core will contract. Contraction will raise the temperature. For a while, that will speed up fusion in a shell around the now helium core. The outer layers heated by this shell burning will expand. The sun will swell into a red giant, its surface reaching out past the orbit of Mars. Earth, if it survives, will be scorched. Oceans will boil away. The atmosphere will strip off into space. The surface will melt into lava. In about 5 billion years, our planet becomes uninhabitable, cooked by the dying star that once gave it life. Eventually, the core will get hot enough, about 100 million degrees, to fuse helium into carbon. 3 helium nuclei combine through the triple alpha process, forming 1 carbon nucleus. That will provide a new source of pressure. For a while. But helium fusion is less efficient. It produces less energy per reaction, and the sun doesn't have enough mass to compress the core hot enough to fuse carbon into anything heavier, so when the helium runs out, fusion stops. Gravity wins. The outer layers drift away, forming a planetary nebula, glowing shells of gas, expanding outward, lit by the ultraviolet radiation from the exposed core. The core itself collapses into a white dwarf, a hot, dense ember about the size of Earth, but with half the sun's mass, slowly cooling over trillions of years. That's the fate awaiting our Sunday, and billions of other stars like it. But for stars much more massive than the sun, 8 times heavier or more, the story goes further. Bigger mass means stronger gravity. Stronger gravity means the core can collapse hotter. Hot enough to fuse carbon into neon and magnesium. 200 million degrees. Neon into oxygen. 1 billion degrees. Oxygen into silicon. 2 billion degrees. Silicon into iron. 3 billion degrees. Each stage produces less energy than the last. Each stage burns faster. Hydrogen fusion might last 10 million years. Helium fusion, 1 million years. Carbon fusion, 1,000 years. Neon fusion, 1 year. Oxygen fusion, 6 months. Silicon fusion, 1 day. The star becomes an onion. Layers of different elements, each burning at different temperatures. Iron core at the center. Silicon shell around that. Oxygen shell. Neon. Carbon. Helium. Hydrogen at the outermost edge, still burning quietly while the core races through its final fuel. Then the core is iron. And iron won't fuse. Fusing elements lighter than iron releases energy. The nucleus formed is more tightly bound than the nuclei you started with. so mass gets converted to energy. But fusing iron consumes energy. Iron is at the bottom of the nuclear binding energy curve. You can't get energy out of it. You'd have to put energy in. The star has reached the end of the line. The core sits there, an iron ball, roughly the size of Earth, but with about 1.4 times the mass of the Sunday. No fusion. No outward pressure. Just gravity pulling inward with nothing to resist it. The temperature is billions of degrees, but that's not enough to change the fundamental problem. Iron won't fuse. The thermal pressure from all that heat can support the core for a while, but the star is actively cooling the core by radiating neutrinos, ghostly particles that barely interact with matter and carry energy away at the speed of light. The support weakens. Gravity presses harder. The core becomes unstable. In less than a second, the core collapses. Electrons get squeezed into protons, forming neutrons and releasing a flood of neutrinos. The collapse continues. The core shrinks from thousands of kilometers across to tens of kilometers in a fraction of a second. Free fall but inward. Gravitational acceleration measured in millions of Gs. Matter falls inward at speeds approaching 1/4 the speed of light, 75,000 kilometers per second. The entire core, more massive than the Sun, implodes faster than sound can travel through it. Then the neutrons resist. Quantum mechanics says you can't pack fermions particles like neutrons too tightly. Pauli-exclusion principle. Degeneracy pressure, a purely quantum effect, not thermal, not electromagnetic, just quantum, pushes back. The collapse halts. The infalling material, racing inward at 1/4 the speed of light, suddenly encounters this rigid neutron core. It rebounds. The shockwave created by that rebound tears outward through the star's outer layers at 50,000 kilometers per second. The star explodes. A supernova. For a few weeks, it shines as brightly as an entire galaxy, billions of stars combined. The explosion is so energetic it creates elements heavier than iron, gold, platinum, uranium. All the heavy elements in your body, in your electronics, in the Earth itself, were forged in supernova explosions. The gold in your wedding ring came from a neutron star collision. The calcium in your bones came from a supernova. The iron in your blood came from a dying star that exploded billions of years ago. You are made of stardust, quite literally. And what's left behind is a neutron star, 20 kilometers across, 1.4 to 2 solar masses. Gravity so strong that a teaspoon weighs 1 billion tons. Or if the original star was massive enough, more than about 20 solar masses. Even neutron degeneracy pressure can't stop the collapse. Gravity wins completely. The core shrinks past the neutron star stage, past any possible state of matter that can resist. It collapses through its own event horizon. It becomes a black hole, a region where space-time curves so steeply that nothing, not even light, can climb back out. The escape velocity exceeds the speed of light, and since nothing can move faster than light, nothing escapes. Gravity didn't just shape these objects. Gravity is these objects. They exist only because gravity refused to stop pulling. Inside a black hole at the singularity, the equations break down. Density becomes infinite. Space-time curvature becomes infinite. General relativity predicts its own failure. We don't know what happens there. We need a theory of quantum gravity to describe it. And we don't have one yet. But we know the black hole exists. We've seen them. Not directly, they're black after all, but through their effects. Gas swirling into them heats up to millions of degrees and glows brightly in X-rays before disappearing past the event horizon. Stars orbiting them follow elliptical paths that reveal the mass and location of the invisible partner. The Event Horizon Telescope even imaged the shadow of a black hole in galaxy M87, the silhouette created where light gets bent around the event horizon. And all that energy, the light from stars, the explosions of supernovae, the heat that makes planets habitable, the atoms that make up your body, comes from gravity's relentless inward push, resisted by the pressure of matter and energy, trying to hold themselves up. The universe is a war between gravity pulling in and everything else pushing out. Most of the time they fight to a draw. Stars burn, planets orbit, galaxies spin. Sometimes gravity wins. Sometimes it wins so completely that it creates the most extreme objects in existence. But gravity does something stranger still. It doesn't just pull through space, it warps time itself. And that warping leads to phenomena so bizarre they sound like science fiction. Clocks that run at different speeds depending on where you are. Satellites that need relativity corrections, or they'd be useless. And orbits that aren't really hovering at all, they're just falling forever in the most elegant way possible. Every 90 minutes, the International Space Station completes one orbit around Earth, 28,000 kilometers per hour, fast enough to cross the United States in 10 minutes. Fast enough that if you could somehow stand on it and throw a ball forward, the ball would orbit independently. But the station isn't flying, it's falling. Every single moment, gravity pulls it toward Earth's center. Every single moment, it accelerates downward. And every single moment, Earth's curved surface drops away beneath it at exactly the same rate. It's falling around the planet, perpetually, forever. That's what an orbit is. Not hovering, not floating, falling but moving sideways so fast that the ground curves away before you reach it. An astronaut on the ISS is also falling. They fall at the same rate as the station. So relative to the station, they don't move. They float, not because there's no gravity, but because they and the station are falling together. On the ground, things are different. The floor pushes up on your feet. That upward force exactly cancels gravity's downward pull. You feel weight. You experience gravity not as a pull, but as the floor preventing you from falling. In orbit, there's no floor. Nothing pushes up. Gravity accelerates you and the station downward at the same rate. You fall together. The sensation is identical to floating, but you're not floating, you're plummeting. This isn't just a clever trick of physics. It's a fundamental insight into what orbits are. Isaac Newton understood this 350 years ago. He described a thought experiment: fire a cannon from a mountaintop. The cannonball arcs through the air and hits the ground some distance away. Now fire it faster. It goes farther before landing. Faster still, farther still. At some critical speed, about 28,000 kilometers per hour at low Earth orbit altitude, the cannonball would travel so far horizontally that the ground curves away beneath it at the same rate it falls. It never hits. It just keeps falling forever in a circle around the planet. That's an orbit. It's not magic. It's just falling done at exactly the right speed and angle. And the strange thing is, this means astronauts are constantly accelerating toward Earth. Acceleration is a change in velocity, and velocity is a vector. It has both speed and direction. Even if your speed stays constant, if your direction changes, you're accelerating. In orbit, you're constantly turning, always curving toward Earth, always accelerating. At 9.8 meters per second squared, the same rate as if you were falling from a cliff. But because you're moving sideways so fast, you never get closer. You just keep falling in a circle. Now add relativity. GPS satellites orbit much higher than the ISS. At an altitude of 20,000 kilometers, gravity is weaker. Not much weaker, about half the strength at Earth's surface. But weaker enough to matter. And in general, relativity, weaker gravity means faster time. A clock in orbit ticks faster than a clock on the ground, specifically about 45 microseconds faster per day. But wait, special relativity says moving clocks tick slower, and GPS satellites are moving fast, nearly 14,000 kilometers per hour relative to Earth's surface. Time dilation from motion slows them down by about 7 microseconds per day. Net effect: 45 minus 7 equals 38 microseconds per day faster. That sounds tiny. 38 millionths of a second. Barely noticeable. But GPS works by measuring the time it takes for radio signals to travel from satellites to your receiver. Radio waves move at the speed of light, 300,000 kilometers per second. A timing error of 38 microseconds translates to a position error of about 11 kilometers. Without correcting for relativity, GPS would drift by 11 kilometers per day. After 2 minutes, your location would be wrong by hundreds of meters. After a week, it would be useless. So engineers built the correction in. Before launching the satellites, they adjusted the clocks to tick at 10.22999999543 MHz instead of the standard 10.23 MHz. slower by a factor of 4.47 times 10 to the negative 10th. That way, once in orbit, once general relativity speeds them up and special relativity slows them down, they tick at exactly the right rate. They stay synchronized with ground clocks. Every GPS satellite is a flying laboratory testing Einstein's theories. Every location your phone shows you is proof that gravity bends time. And near stronger gravity, the effect becomes impossible to ignore. On the surface of a neutron star, time runs about 30% slower than in flat space far away. An outside observer watching someone on the surface would see them moving in slow motion. Meanwhile, the person on the surface would see the universe around them sped up. Near a black hole, it gets extreme. At the event horizon, the boundary where escape velocity equals the speed of light, time dilation becomes infinite. From the perspective of someone far away, anything falling toward the horizon slows down asymptotically. It takes forever to cross. You'd see the object freeze, fade, red, shift into invisibility, but never quite disappear. From the perspective of the falling object, though nothing special happens at the horizon. You cross it in finite time on your own clock. You keep falling inward toward the singularity at the center. Time continues normally for you. Both perspectives are correct. Time itself becomes relative. Your now is not the same as someone else's now if you're in different gravitational fields. This isn't philosophy, it's measurement. Atomic clocks are precise enough to detect time dilation from height differences of just 30 centimeters. Climb 1 foot and your clock ticks faster. Not by much, but measurably. In 2010, physicists at NIST ran 2 atomic clocks at heights that differed by about a foot 33 centimeters. The clocks ticked at slightly different rates. The difference matched Einstein's predictions exactly. Gravity doesn't just pull objects together. It warps the flow of time itself. The deeper you are in a gravitational well, the slower your clock runs relative to someone higher up. And this leads to something even stranger, gravitational waves. When massive objects accelerate, when 2 black holes spiral together and merge, or when a supernova explosion throws matter asymmetrically, they shake spacetime itself. Ripples spread outward at the speed of light, compressing and stretching space as they pass. In 2015, the LIGO detectors in Louisiana and Washington state felt one of these ripples. 2 black holes, 29 and 36 times the sun's mass, orbiting each other faster and faster, spiraling inward. In the final fraction of a second, they merged. The collision released more energy than all the stars in the observable universe combined for a brief instant. The gravitational wave from that merger traveled outward. 1.3 billion years it traveled. By the time it reached Earth, it had weakened to almost nothing. It stretched and squeezed space by about 1 part in 10 to the 21st. That's roughly the width of a human hair compared to the distance to the nearest star. LIGO detected it. 4-kilometer-long laser interferometers sensitive enough to measure changes smaller than a proton's width saw spacetime itself ripple. 3 scientists won the Nobel Prize in 2017 for that detection. Because it wasn't just finding a new phenomenon. It was confirming Einstein's century-old prediction, proving that spacetime is a real physical thing that can vibrate like a drum. Gravity isn't just a force pulling objects together. It's the shape of the universe, curved spacetime. And that curvature affects not just where things go, but when they arrive. But gravity does more than bend time and warp space around individual objects. At the largest scales, across billions of light years, gravity shapes the very structure of the cosmos. It decides where galaxies form and how they move. It builds invisible scaffolding that holds the universe together. And it's locked in an eternal tug-of-war with something even stranger: dark energy. In 1977, astronomer Vera Rubin was studying spiral galaxies, specifically how fast stars orbit around their centers. Physics makes a clear prediction. Most of a galaxy's visible matter stars gas-dust clusters near the center, so gravity should be strongest there. Stars close to the center should orbit quickly. Stars farther out, where there's less mass pulling on them, should orbit more slowly. That's how our solar system works. Mercury races around the Sun every 88 days. Neptune takes 165 years. The farther from the Sun, the slower the orbit. But when Rubin measured galaxies, she found something else. Stars near the edge of a galaxy were moving just as fast as stars near the center, sometimes even faster. The rotation curve, a plot of orbital speed versus distance from the center, was flat. That shouldn't be possible. Unless there's more mass than we can see. A lot more mass, distributed in a huge halo surrounding the visible galaxy. Rubin calculated the numbers. To explain the rotation speeds, she observed galaxies would need about 10 times more mass than the stars, gas, and dust we could account for. 10 times. 90% of a galaxy's mass was invisible. She wasn't the first to suggest this. In 1933, Fritz Zwicky studied the Coma Cluster, a group of over 1,000 galaxies bound together by gravity. He measured how fast those galaxies were moving. Too fast. Far too fast. If only the visible matter existed, the cluster's gravity wouldn't be strong enough to hold it together. The galaxies should have flown apart billions of years ago. Zwicky estimated the cluster needed about 100 times more mass than what he could see. He called it dunkle materie, dark matter. For decades, most astronomers were skeptical. Maybe we'd miscounted the stars. Maybe there were dim objects we couldn't see, brown dwarfs, black holes, planets. Maybe gravity worked differently at large scales. But Rubin's work, combined with decades of further observations, made the case undeniable. Every galaxy rotates too fast. Every galaxy cluster holds together too tightly. Everywhere we look, gravity is stronger than the visible matter can explain. The conclusion: about 85% of all matter in the universe is dark. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. We know it exists only because of gravity. It's there. We can measure its effects. We can map where it is. But we can't see it, and we don't know what it's made of. And it's everywhere. Woven through galaxies, wrapped around galaxy clusters, spread across the cosmos in vast filaments and sheets, forming a structure cosmologists call the cosmic web. You can see it, not the dark matter itself, but its effects through a phenomenon called gravitational lensing. Light travels in straight lines through flat space. But space-time isn't flat. Mass curves it. When light from a distant galaxy passes near a massive object, like a galaxy cluster, its path bends. If the alignment is right, you can see multiple images of the background galaxy, or arcs, or rings. The foreground mass acts like a lens, warping the light into strange, beautiful shapes. By measuring how much the light bends, you can calculate how much mass is doing the bending. And almost always, it's much more than the visible matter accounts for. In 2006, astronomers observed something extraordinary. Two galaxy clusters, called the Bullet Cluster, had collided and passed through each other. The hot gas in each cluster, visible in X-ray images, interacted. It slowed down. Most of it ended up between the two clusters, trailing behind like wreckage from a crash. But gravitational lensing showed that most of the mass wasn't there. Most of the mass was with the galaxies themselves, which passed through the collision largely unaffected. Because dark matter doesn't interact with normal matter except through gravity. It just sailed through. The Bullet Cluster is direct evidence that dark matter and normal matter are separate things. They behave differently. They can be in different places. And simulations of the universe's evolution, starting from the conditions 1 second after the Big Bang and running forward for 13.8 billion years, only match what we observe if you include dark matter. Without it, galaxies don't form fast enough. Structures don't clump together properly. The cosmic microwave background, the leftover radiation from the early universe, wouldn't have the temperature fluctuations we measure. Dark matter isn't a patch to fix an equation. It's a necessary ingredient. The universe doesn't make sense without it, and it forms structure, long, thin filaments connecting nodes where galaxy clusters sit, empty voids in between. If you could map all the dark matter in the universe, it would look like a three-dimensional spiderweb stretching across billions of light years. Galaxies form where the dark matter is densest. They sit on the filaments like dewdrops on silk. The web provides gravitational scaffolding. Normal matter falls into the wells, collapses, lights up as stars. But the dark matter stays invisible, holding everything together. We live in a galaxy held together by something we can't see. orbiting a star that orbits a center of mass composed mostly of matter we can't detect, swimming through an invisible ocean that outweighs everything we've ever touched by a ratio of 5-1. And the strangest part, even with all that dark matter, gravity is still losing. In 1998, two teams of astronomers were studying distant supernovae. Type Ia supernovae exploding white dwarf stars all have roughly the same brightness. That makes them useful as distance markers. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it is. The teams measured distances to dozens of supernovae, and they measured how fast those supernovae were moving away from us via the redshift of their light. They expected to find that the universe's expansion was slowing down. Gravity pulls galaxies together, so the expansion that started with the Big Bang should gradually decelerate, maybe even reverse someday, pulling everything back into a big crunch. Instead, they found the opposite. The expansion is accelerating, speeding up. Galaxies far away are receding faster than they should be. The universe isn't just expanding, it's expanding faster and faster. Something is pushing outward, something opposing gravity's inward pull, something that makes up about 68% of the universe's total energy. We call it dark energy. We have no idea what it is. It's not matter. It's not radiation. It's something else. A property of space itself, maybe. A cosmological constant in Einstein's equations. A quantum field permeating the vacuum. Whatever it is, it's winning. On small scales, solar systems, galaxies, even galaxy clusters, gravity dominates. Dark matter and normal matter clump together, held by their mutual attraction. But on the largest scales, across billions of light years, dark energy dominates. It pushes space apart. The farther apart two points are, the faster they separate. The result, the cosmic web is stretching. Galaxy clusters are drifting apart. In the far future, hundreds of billions of years from now, the expansion will have carried most galaxies so far away that their light will never reach us. The universe will grow cold, dark, and empty. Stars will burn out. Black holes will evaporate through Hawking radiation. Even matter itself might decay. The cosmos will approach maximum entropy, a state of perfect, boring uniformity. Gravity built everything we see. Stars, planets, galaxies, the cosmic web. It clumped matter together against the expansion of space, creating islands of complexity in an otherwise smooth universe. But gravity can't win forever. Dark energy ensures that the expansion will continue. The structures we see now are temporary. Gravity and dark energy are playing a game. For now, gravity has created wonders. 13.8 billion years of structure formation, galaxies, stars, planets, life. But dark energy is patient, and in the end it will stretch everything so far apart that gravity can't hold anything together anymore. Still, for now, in this brief moment of cosmic history, gravity is shaping the universe. Building, sculpting, holding together everything we know. Every sunrise exists because gravity compresses hydrogen into fusion. Every planet orbits because gravity bends space-time. Every galaxy rotates because dark matter's gravity holds it together. Gravity is the architect. Invisible, relentless, everywhere. It dictates the dance of planets and the death of stars. It slows time, bends light, and holds the universe together against the void. And when you stand on Earth, feeling that gentle pull toward the ground, you're feeling the same force that shapes galaxies. The same curvature of space-time that bends light around black holes is in a tiny way bending space-time around you. You're part of it, connected to it, shaped by it. Gravity is not a single thing. It's a spectrum, a shapeshifter, gentle on Earth, crushing on Jupiter, inescapable at a black hole. It changes form depending on where you are and what's nearby. But everywhere, it's there, pulling, bending, connecting everything to everything else. That's the diversity and unity of gravity. Different everywhere. But everywhere the same fundamental force warping space-time, guiding matter, building the universe. And it all started with that pull you felt at the beginning. That weight pressing down on your shoulders. That invisible hand keeping your feet on the ground. Now you know what it really is.